Alright, hello, hello. Let's shut off my sound before I get echo. And cool. Should be live now. This stream is going to be doing volume of cross sections, and we're going to be kind of reviewing some of the area questions off of the most recent homework. That's where I was going to start off. I kind of looked through and saw what people were missing and put together this set of 3 questions that were the most commonly missed questions. So that's where we're going to start off. Just a moment. Wait a little bit for show up. Hello, Aspen. Drew. Hey, Chelsea. Hello, Caitlin. Hi, Michael. Hello, Isla. Welcome, welcome. Welcome, Matthew. you did the homework. Hooray! Yeah, people did really well on this homework on average. I was looking in at scores, and there were a lot of people in the 80% or above category. So that was pretty sweet. Seems like area was not an issue for most folks. That's good. You may notice in the bottom right that I still haven't activated Windows. I haven't gone to school yet, which is really what that is. I was gonna go last week, and I got we ended up going to a different Indian food restaurant to pick up from that wasn't closer to school, so I didn't end up going to school. But I did get Indian food, so that was good. Hello, Andrew. Welcome. All right, let's get started with talking about these. So, the first question that was interesting, which was actually the last question of the ones on the list that I will talk about, in its chronological order in the assignment. But it says the area of the shaded region in the figure is represented by which of the following integrals? The thing people got baited by is that this b doesn't matter at all, because where it goes to the x-axis is absolutely irrelevant. Like, if I took this exact same shape and moved it up over here, so same 2 curves, just shifted over, and I know I drew a crappy drawing, but pretend these 2 things are exactly the same. If this is here and this is here, it doesn't matter because they have the same area between them in either spot. So the fact that it goes through here doesn't matter, and B is a totally irrelevant point. So I actually don't care about B at all, which means A is where these start and C is where these end. So all I'm looking for is an integral from A to C, which means get rid of all the ones, whoops, that one's fine, that have any other integral stuff going on. That isn't just A to C. And then the other thing was, top curve is always f of x, bottom curve is always g of x, so it's just f of x minus g of x, which is why it's just d. This was not the first question on the homework. I think this was like the 6th question on the homework or something. And hello, Keith, and hello, Elizabeth. Welcome. Okay, second question that had a fair number of missed at-bats here. What is the total area of the regions? Hint, regions. This is what most people did wrong on this. Between the curves y equals 6x squared minus 18x and y equals negative 6x from 1 to 3. So let's pretend you don't have a calculator for this. If you see regions, think that these are going to meet somewhere on that interval, which means I should set negative 6x equal to 6x squared minus 18x and solve for where they meet. If I add 6x to both sides, I get 0 equals 6x squared minus 12x. We factor out a 6x, and we get x minus 2. Oh, 2 and 0. These meet at 2 and 0. Now 0 is irrelevant because it's not on our interval. But since these meet at 2, I know I'm going to have to do two different integrals. I'm going to have to do the integral from 1 to 2 of crud, which one's on top. Turns out there's an easy way to figure out which one's on top here. You just plug like 1 into both of these. And if you do that, you get negative 12 in this one and negative 6 in this one. So the line's on top. Cool. Negative 6x minus 6x squared minus 18x. And then you just integrate from 2 to 3, and the other one's on top after this point, so it's 6x squared minus 18x minus a negative 6x, like so. And then you're basically ready to rock and roll and integrate this thing. You could have also done this and saved yourself the hassle of doing these two different integrals. You could integrate from 1 to 3 and just say it's the absolute value of negative 6x minus 6x squared minus 18x, like so. And this would also get you to the promised land of 12 here. So where this went wrong for most people was figuring out where these meet. Also, it's really easy to tell where these meet if you just graph them in Desmos. So, subtle reminder, where's my internet? There it is. Desmos. And you can just type in negative 6x and 6x squared minus 12x minus 18x. What was the problem? I think it's 18x. Oh gosh, I didn't remember what the problem was. Feels bad. 6x squared minus 18x and negative 6x. Cool. So we can see they meet at 0, which check, and we can see they meet at 2 here. And so that was the other way to figure out where they meet. And we can see the line is on top from 1 to 2, and then the curve is very much on top from 2 to 3. Why can we do the absolute value one? Because if you're always finding the absolute value of the distance between the curves, so the absolute value one looks something like this. Really, it's what you're integrating is always the distance between the curves, and you want that to always be positive to do area. And so if you absolute value it, it's always positive. So if I do that, like so, close absolute value dx. Oh gosh, what just happened? There we go. Then you get 12, and that's the right answer, which is the same answer you get if you plug in that initial full integral I did. So I showed a ton of different ways to do this one. You only needed to pick one of them. You didn't need to do all these things. If you came to Desmos, it turns out this was pretty easy. If you use absolute values and you have a computer algebra system like a Desmos or a graphing calculator, then you're in pretty good shape for doing area, because if you use an absolute value for the whole inside, you always get area. So that's pretty cool. All right, the last one there was an issue on was this one right here. And I'm pretty certain I know what the issue is. So if you graph these, it turns out sine's on top and e to the x minus 2 is on the bottom. So this is just the integral from 0 to the point where these things meet. And I did this one earlier. It's like 1.054-ish. Of top curve minus bottom curve, sine of x minus, and here's where the issue comes for a lot of people. When you subtract e to the x minus 2, you need to make sure you use parentheses around the whole thing. Because a lot of these other bait answers were ones where if you said minus e to the x minus 2 like this, you would have gotten it wrong. It's actually a plus if you distribute that negative sign. And that's where a lot of people went awry. Otherwise, people use like 1 as an one of the bounds there, and that was the other problem for folks. But this sign was always on top from 0 to 1.054 here, which is where they meet. And that was that one. So those were the hardest questions on the homework by miss rates. No, I do not want to keep my ink annotations. All right. Now we are talking about some new stuff. So this is actually some real new stuff here. We're talking about cross-sectional volumes. And this is a little bit of a difficult one to visualize, especially if you're not a super visual thinker. We're going majorly into geometry land. So actually, what we're doing for the rest of this class, I guess, is we're going to be integrating different geometry formulas from, from the class, like pi r squared for a circle. That's going to be an equation we're integrating. We're going to integrate, side squared for a square. That's something we're going to integrate. What else? 1/2 base times height. And what we end up integrating, which one of these we integrate, depends on what this thing looks like when it's translated into 3D. So as a 2D graph, the semicircular thing that we're looking at, just looks like a pi wedge, like something like this. Or on an XY plane, something like this. So just a line with a negative slope. And then what we're doing is to go into 3D, we're putting semicircles like this. So the diameter goes from across the y distance on this. And we're just doing an infinite number of these semicircles and finding the area of this thing. You said take notes today, right? Crud muffins. I forgot. Yeah, so that means I have to get the notes ready. So I will get that ready in a second. There will be a slight interlude in a minute. But this is more the intro part, so you don't need to take notes yet. Okay, so discard those changes. Because this is more the part where I'm talking big picture about things, and oopsie daisy. Okay, so here's some more examples. All of these have a base curve of y equals x squared, but all of these have different shapes. So in the first shape area up here, we have squares. And so it's y equals x squared, but that y distance is the base of a square, and we're having an infinite number of those, and that makes a kind of weird looking shape. I don't even know how to describe that thing. If we use triangles instead, which is happening in the second picture, we're making a 3D shape with those triangles that looks like a kind of sloping pyramid sort of thing. If I use semicircles, it makes a weird funnel. This looks like a musical instrument. And if we use rectangles, it looks something like this. Imagine these as smooth 3D shapes. The granularity of these is just to like show visually what they look like. And if you want to look at what these look like in actual 3D, I have this tool. So this is just using Wolfram Alpha stuff. So my base region is a square here. So this is going to be the base of all my shapes. And if I use squares going up into 3D and rotate this dude, this is what it looks like. So there's the squares. And the squares are going just related to these lines, so it just cuts the shape at a whole bunch of different spots. And then put squares into 3D, and what it makes is this, I guess like bishop hat sort of thing. So we are not rotating here, correct. What we are doing is just putting a shape up into 3D. So I'm taking this base, which is a circle, and for every width of this base here, I'm making a square that goes up. And this shows a finite number of cuts, like, I don't know, 15 cuts or something. But in reality, when it makes the shape, there's a roughly infinite number of cuts, which is why it has like smooth edges like this. So if I use equilateral triangles instead of squares, it makes something like this. I don't know what this is. It looks like a piece of candy. If I use semicircles, it very boringly makes a hemisphere. Or, a half sphere. And if I use rectangles, it makes something that looks very similar to the squares. Squares and rectangles look pretty similar, so it makes a much shorter hat. Now, when we start changing the base, things get a lot more exciting. So a circle base is pretty boring shape-wise. It makes fairly uniform shapes. Squares, also fairly boring. Like, wow, we made a box. Good job, us. Wow, we made a tunnel. Good job, us. But when we start making the bottom something like, you know, a quadratic and a line like this, things get a lot more exciting. Like this creates like a shell with semicircles. If I use rectangles, it creates a very weird looking shape. Equilateral triangles, perhaps an even weirder looking shape here. You can see the triangles. If we look at it from this angle, all of those are triangles. You can see the base shape. If we look at it from this side, it's rotated. But in 3D, it makes some weird looking stuff. And then the undulating is probably the weirdest of all. Even squares with undulating makes like a really cool pillar. Or honestly, I always think that these ones here look like some ships from Star Wars or something. And so these are some weird things. So again, node rotation's happening here. We're just putting 2D shapes, like transposing them up into 3D. So it's like in this picture here, and I'll edit the screen here, it's like we're taking a triangle and putting it up into 3D here, and then putting it up into 3D here. And the resulting shape is the shape that's created when you put all those triangles up into 3D based on the different bases. So when the curves get closer together, our triangles are smaller, and when the curves are farther apart, our triangles are bigger. Are the shapes hollow? They're only hollow because that's how this rendering software works. Technically, the shapes would be filled. They just want you to be able to see the the dimensions of it from all the angles. So they are not hollow. This creates like a cool like half face, like that. It's very pretty. And further more stuff like that. So these are visually what these shapes look like. And so this kind of symmetry, this kind of shape symmetry, is useful for finding the volumes of a lot of non-uniform shapes. And so the fact that we can find uniformity out of things that look like they're not uniform is part of what makes calculus so powerful for finding volumes, which is why we use it. Okay, so I need to unplug my mic for a minute to pull up the notes because I goofed and wasn't ready for this, but I'll be ready in a minute. So 1 minute interlude. All right, interlude over. Let's make sure mic is working. It is. Hooray. Hello, Elise, and welcome. You're in time for our notes. So thank you for reminding me. I believe Nick gets credit for that. So I appreciate it. Let's just mob it here. So let's take a look at how to do one of these, and then we'll go back through and fill in the steps, because I like doing the steps after we've looked at a question first. So, in our first question here, we say the base of a solid is enclosed by y equals x and y equals x squared. So, what that means is this region is the base of our shape between the two curves. A solid is formed with cross-sections perpendicular to the x-axis. That means that the base of our squares are this direction, and they go up into 3D. The side you're perpendicular to actually does matter, because if we look at it, the triangles would be wider actually going this direction, because it's wider from left to right than it is from up to down. So we actually get two different answers if we go either way. Because we're in the x direction, it actually makes this problem easier, because top curve minus bottom curve is how we find the distance between those two curves, the base of our shape. Now, I told you we were integrating area formulas. So what we are going to be doing is, in this case, because we're trying to find squares, we're going to be integrating sides squared. The challenge of this problem comes from figuring out what the side is, what our bounds are, and all that kind of stuff. So the side in this, the sides of our square is top curve minus bottom curve, which in this case is x minus x squared. Because our side is determined, is in terms of x, I'm going to use x as my bounds. So I'm going from 0 to 1, where these two things meet. So I can rewrite this integral as the integral from 0 to 1 of side squared, but instead of writing side, I'm going to write x minus x squared dx. And that's it. So I took the square formula, plugged in what the side length was based on my picture, and then just integrated from the bounds given to me again in the picture. So in order to integrate this thing, I actually have to expand out x minus x squared, and I get x squared minus 2x cubed plus x to the fourth. I integrate this, and I get x cubed over 3 minus 2x to the fourth over 4 plus x to the fifth over 5, evaluated at 0 and 1. And then we just put 1 and 0 in there. And the answer, because 0 just gives us 0 in this integral, is 1/3 minus 1/2 plus 1/5. So that's not very big, because 1/3 is like 0.333, 1/5 is 0.2, and if we subtract a half from 0.533, we get 0.0333, which is tiny, or like 1/30th, which we could also get by converting these all to a bottom of 30, and we get 10 over 30 minus 15 over 30 plus 6 over 30, which is 1 over 30. So that's a tiny volume. So this shape that's created by putting squares up for the difference between x and x squared is not a very big shape. It's pretty tiny, and its volume is 1/30th. Don't see any questions right now, so I'm guessing people are writing stuff down. Kind of wanted to pause here and see if there are any questions. How does the square of one side get volume? Okay. If you're curious how we're getting volume out of just the formula, side squared is area. If I integrate area, it's like adding another dimension. I'm taking an area and putting it into 3D by integrating across this x distance. And so it's like 1 dimension, 2 dimension, 3 dimension, and that gives us volume. So that's kind of the physical or the equation-y version of it. The physical version is instead of just integrating the distance, we're integrating the area of the square across all that interval. So what we're integrating is actually all of these squares across this entire thing, and that is getting us volume through the actual visual method. All right, so let's go up and do our words now that we've seen an example of this. Steps for finding this method. Find the correct area find the area equation for your cross section. And yes, Nick, you're basically taking an area equation and putting it in 3D by integrating across X. Because the squares are going up into like Z as their dimension. Okay, and the cool part about this is the area equation for your cross section is basically always going to be one of these. So there aren't that many area equations, and you know almost all of these. The only ones that are a little questionable are the triangle ones, like circle, pi r squared, semicircle, 1/2 pi r squared, rectangle, base times height. Yeah, okay. Square, side squared, easy. Equilateral triangle, if you're wondering why it's √3/4 side squared, it has to do with actually how you find the area of an equilateral triangle, which is if you cut it in half, it makes a 30, 60, 90, like so. We know that each of the long sides is side, which means if I cut this in half, this is half side. And this is the √3/2 side, so √3/2 side. And all I do to find the equation of this thing is I do 1/2 base, but my entire base is S side, at times height, which is this √3/2 side. And booyakasha, we got √3/4 side squared. If we do it with a volume equation, are we going into the fourth dimension then? Yes. Just good luck defining what that means a lot of the time. Although you do end up doing some of that stuff later on, like with time. So you're integrating into the time dimension with a volume. So yes, this translates up further, but we don't go farther than this. And then the fifth dimension. Yes. All right. So hopefully you're okay with a lot of these. Isosceles is actually even easier because to justify even, because isosceles means these two sides are the same and the hypotenuse is √2 times side, so it's a little longer. And base and height are just S, so it's 1/2 S times S in this case, which works out really nicely as 1/2 legs squared or 1/2 side squared. Let me know if this is anywhere close. S is side, S squared is area. Integral of S squared is to find volume. Yes. Kelly, that is right. Yes. All right. So that's where all these area equations come from. This is all just basic geometry stuff, maybe even algebra 2 stuff. I'm not sure which class they start moving into this world. But the idea is these are the only area equations you will need to do these questions. So the next at bat here is to use the functions given to you to represent the, whoops, I'm still on eraser, the side or base or leg. So the stuff you need in your equation, side, base, height, whatever, things you need to define in your area equation. And so that's when we plugged in down here, x minus x squared for the side length. That was exactly that step. And now the caveat that we haven't quite gotten to yet with problems, but that B will make us do when we do it, is you may need to rewrite equations the reason why you would need to rewrite them is if it's perpendicular to the y-axis, you need your equations as like x equals an equation of y. So you may need to rewrite equations for the other variable. For the other variable. Integrate is that step we just get to say, hey, integrate it. Cool. And then last piece is solve for the volume. And don't forget, there could be units. Units, maybe. Yeah, I also, yes, I do definitely have this notes on my website, and I talk about all of these things there. So you can consult that if you need. All right, let's move forward to another example, notably one where we have to go in the y direction. So looking at B. I'm going to zoom in on this guy for Liam's sake here. And everybody like Liam who didn't speak up. And here we have a base of a solid enclosed by y equals 9 minus x squared, x equals 0, and y equals 0. So that is this shape. So this is a interesting one. It looks like it goes to 3 over here. That sort of thing. It goes up to 9 up here because it's 9 minus x squared. So just kind of putting the endpoints on this. And it says, a solid is formed with isosceles triangles whose hypotenuse is perpendicular to the y-axis. Okay, so this one added a little bit of weirdness to us, because unlike our area equation up above, so up here, we don't get the base just from this problem. What we get is that the hypotenuse of these isosceles triangles is perpendicular to the y-axis, which means that's our hypotenuse, and our isosceles triangle goes up into 3D like meow, and we have those two sides being equal, which is why it's isosceles. So I'm going to draw another one of these because I just realized how horrible this looks. There we go. So that's what these little triangles look like. I put those little marks on them. If you remember from geometry class, they have the same number of marks on them. It means they are equal. And I guess since these are definitely aren't equal to those ones up there, I should put 2 marks on this. Wow. That Wyatt Waters? Wonder who that Wyatt is. Anyways, moving forward. So I'm gonna have to. Well, okay. I'm gonna write my volume equation. I know it's gonna be 1/2 base squared in this, but base is not this distance. Base is these sides, these isosceles pieces, the 2 parts that are equal. So I'm gonna have to go through a little bit of extra work to figure this out. I already have some opening work here, which is that this distance is not this distance. It's not y equals 9 minus x squared, because that is the up and down distance to the curve. It's actually this equation rewritten and solved for x. So this is one where y minus 9 equals negative x squared. I can subtract 9 from both sides. I can multiply by a negative. 9 minus y equals x squared. And then I can square root, and I get x equals the square root of 9 minus y. I have to usually think about plus or minus here, but because our x values are positive everywhere in this picture, I don't need the negative one, so I can just keep the positive root 9 minus y. All right. So now that we have this, I now know my hypotenuse, but my hypotenuse is not my side length, is not my base. If you remember, This, the way we label these is this is like base, base, and this is base root 2. So to find, if square root of 9 minus y is my hypotenuse, then all I do is divide it by the square root of 2, and I get my actual base. So now that we have these, I can put this stuff in, root 9 minus y over root 2 in for b. And I get 1/2 root 9 minus y over root 2 squared. And this time, since my equation's in terms of y, I'm going to put a dy. And for my bounds, because my equation's now in terms of y, I'm going to go from my bottom y, which is 0, to my top y, which is 9. So, I know there are some distracting folks in chat. Hello, distracting folks. If you could be less distracting, that would be great. But hey, people in my class, do you have any questions about how I got here? Because this one's a little heavier than the ones we've looked at so far. We'll hang out for a little bit. Yeah, I know there are people in here, but I want to stay focused on the math. How did you get B again? Okay, so what I did for B was I needed to find this distance, which is an x distance. This distance is an x. So to find an x distance, I need to solve for x in my equation, which was 9 minus x squared. So that was all this work here, was I solved for x. I figured out x equals the square root of 9 minus y. But this x is not what I used to find the volume of an isosceles triangle, because the hypotenuse is not what gives me the volume. I need to find the two base sides, or the two isosceles sides. And to find those sides, all I do is I take the hypotenuse and I divide by the square root of 2. And that's how I found this here, was I took the hypotenuse distance, which is root 9 minus y, and divided by the square root of 2. Because that side is always root 2 longer, and if you don't know why, it comes from the quadratic formula. So 2b squared equals h squared, square root both sides, root 2b equals h. And that's how you find the hypotenuse side there. Are the bounds 0 and 9 because you were using y instead? Exactly that, yes. So when I went to find the bounds, I needed to make sure they were y's because I was using y. And it all comes from this, which side are you perpendicular to? And it's the y-axis. Cool. All right, so the nice part now, math-wise, is that the square root of 9 minus y squared is 9 minus y. And the square root of 2 squared is 2, which makes this a much easier integral than it at first looks. This is just 1/4 times the integral from 0 to 9 of 9 minus y dy. Alrighty. One sec. I'm just declutterifying the chat. Okay, so now I'm going to integrate, and I'm going to get 9y minus y squared over 2 times 1/4, evaluated at 0, 9, and then we just chuck 9 in there, and we get 1/4 times 81 minus 81 over 2, which is just 81 over 8, or what, 10.125. What is happening? People are distracting chat. So, God bless. But anyways, are there any questions with how this went? I kind of breezed through a lot of the integral steps because they're kind of the less important parts. You guys have a calculator with you on almost all these questions, all of them on the homework because I can't control whether or not you use a calculator. So it shouldn't be too bad to do all these. And I mean, realistically, this was a pretty easy integral. Okay, so let's move forward. We got dos más. Okay. Now we have a base of and solid enclosed by y equals 3x squared and y equals x cubed, so two curves this time. We have equilateral triangle cross sections perpendicular to the x-axis. Okay, so we're back x. So our equilateral triangles are going this direction, like so. Which means the distance between the curves is just a y distance. So all the distance between the curves is top curve minus bottom curve here. All right, so I got to figure out which is the top curve. Turns out this is pretty easy. You just plug one in, you get 3 and 1. Cool, y equals 3x squared is the top curve. So I know that the distance between the curves is top curve minus bottom curve, like so. Now, my equilateral triangle formula is root 3 over 4 times side squared. I guess I don't really need a d whatever for this. I'm going to plug that in when I figure out which side, what the side is. But I already defined the side. The side is just top curve minus bottom curve. 3x squared minus x cubed. So let me plug that in. I'm going to pull the root 3 over 4 out, like so. And do 3x squared minus x cubed squared dx. My bounds are where my x goes from, so now my y would be a pain in the butt because it goes from 0 to 27. But the x's only go from 0 to 3. So this is the integral from 0 to 3. Now we just expand out the squared to integrate it. So if I FOIL this out, I get 9x to the 4th minus 3x to the, 6x to the 5th for the two middle terms. They're each 3x to the 5ths, plus x to the 6th. So all I did between these steps was FOIL this. You're going to fail this class and you don't care. You're not going to fail this class and you probably do care. So I'm very confused by that statement. Anyways, moving forward. Now I can integrate this. I get root 3 over 4 times the evaluated at 0 and 3 of 9x to the 5th over 5 minus x to the 6th plus x to the 7th over 7. I cheated a little bit there, and this was x to the 6 over 6 when I integrate it, which is why I just got an x to the 6, because there was already a 6 coefficient. So I want to step back and review this, because I know I went through this a little quickly. I said equilateral triangle, that's root 3 over 4s squared, which I got from the table up above. I said my side length in these equilateral triangles is, because I'm perpendicular to the x-axis, top curve minus bottom curve just in terms of x's. I figured out which curve was top and bottom by plugging 1 into each of them, and figured out that 3x squared was very much bigger on that interval than x cubed is. So I figured out my side length is 3x squared minus x cubed. Then I just plugged it into the formula. I figured out my bounds were 0 to 3 for x, and that dx was my variable. I FOILed 3x squared minus x cubed, got this, which allowed me to integrate and get this, and now all I'm going to do is plug in 3. All right, I'm going to hide that comment. Aspen, let's try to be a little more appropriate. No expressions that involve the F word, please. All right. And now all we do is plug in 3. And we get root 3 over 4, and there's no way I'm going to simplify this one this time. 9 times 3 to the 5th over 5 minus 3 to the 6th plus 3 to the 7th over 7. And booyah, that's the answer. Done. Oh, people are playing different people. Okay. Curious. Huh. Yeah, there are some people having fun in this. Just ignore those comments, honestly, people. Yeah, okay. Yeah, I know. I know what's going on here. Sorry, folks. Yes, they're creating new accounts in your name. Some real winners here. All right, let's just move forward, and I will read the serious comments in chat. All right, so our last one here has semicircles perpendicular to the x-axis here, which means we get to stay in X-land. Now, that means that our bases of our semicircles are going to look something like this distance. So that's top curve minus bottom curve, and so I know that this distance, the diameter of my semicircles, is going to be top curve x plus 1 minus bottom curve x squared. Yeah, Nick, I could do this in Teams, or I could just make it a private YouTube stream. So that would get around it also. Okay, so moving forward. So what have I done so far? I figured out that this was perpendicular to the x-axis. I drew in these semicircles, and I figured out the diameter of these semicircles is top curve minus bottom curve. X plus 1 minus x squared. Now, diameter is not how I find the area of a semicircle. I find it by finding the radius. So actually, my radius is, and I don't need parentheses anymore, I guess, is x plus 1 minus x squared over 2, like so. Now, what this means is that when I go to integrate this, and what I'm integrating is, since it's semicircles, 1/2 pi r squared, I'm going to plug in r as this, x plus 1 minus x squared over 2. And I'll take the pi out also and just put x plus 1 minus x squared over 2 squared dx, like so. Now, what I'm going to do here is I'm going to square this inside. Now, this one's definitely the biggest pain in the butt of any of these questions because squaring that inside is quite a bit more work than squaring the other insides. First idea here is that the bottom is 2 squared, which is 4. And the top is, and this is where things get a little hairy. I'm going to do a big box method to multiply this out, and x plus 1 minus x squared, and x plus 1 minus x squared, like so. So, x squared, x, negative x cubed, x 1, negative x squared, negative x cubed, negative x squared, and x to the 4th. Guys, don't worry about this. If you ignore the trolls, they go away. So now I'm gonna take all the stuff in the table that I just squared, and I get x to the fourth minus 2x cubed minus x squared plus 2x plus 1. If you're like, Mr. Kennedy, could I have just saved this by typing this into Desmos? Heck yes, you could. But just know that you can't integrate these things without doing this. I need to define my bounds, where this thing starts and ends, and here I really, really, really need Desmos. And Nick, you're no problem. You're fine. All right, moving forward. I'm going to type that into Desmos to solve this question and finish it up here. So, pulling my question up, it is x plus 1 and x squared. Cool. These meet at those 2 points that I just clicked on the graph and then accidentally clicked off of. Oopsie daisy. Oh, whatever. So they meet at what? Negative 0.618 and 1.618. And we can save ourselves a lot of hassle of having to integrate this and all those horrible steps by just saying, okay, so I knew this was semicircle, so it's 1/2 pi times radius squared, and I had figured out that my radius was x plus 1 minus x squared over 2, like mya, dx. Boom, answer done. Feels good. Yeah, I know, Nick. Don't worry, real Nick. I know the hateful comments are definitely not coming from you. Anyways, this saved us a lot of hassle on that question. You are welcome to use Desmos when you're doing this homework. Setting these up is most of the battle. In fact, even on the AP tests, they'll put these as no calculator, questions even as janky as this, and they'll just be like, write but do not solve. And you could just be like, yo, this is A and this is B. I didn't even know how to find these. Integrate from A to B like this. And that's how they did these on the AP test. So really, the bread and butter of these is setting these up and solving them. Yeah, the problem with reporting them is A, YouTube doesn't do anything about it, and B, I want to make sure I'm not reporting the actual right ones, and it's just a pain. So I'm just going to keep ignoring them. Okay. Moving forward. Okay, so that's the notes. This is cross sections. It really is just find your area formula, figure out how to represent the side or the base or the radius in your question. You don't need to square the integral. You don't need to square the integral. Oh! You do need to square the integral. Good save. See, this is why... Oh, wait, what? No, I already... Oh, wait. Oh, yeah, I definitely didn't square the integral. No, you guys were right. So how do I square the integral here? Oopsie daisy. Thank you for the save there, ladies and gentlemen. It's actually quite a bit smaller than I thought. So, hey, good point out, folks. Thank you for making chat useful in spite of everything. Nice work. So yeah, 1/2 pi r squared. R squared is this thing. And thank you for that save. So yeah, it's actually smaller than the integral of the area there, which is what I had found originally. Kind of. The really janky area. So yeah, fantastic work, folks who pointed out those things. I'm going to go back to my PowerPoint real quick. If you're curious about cross-sections uses at all, turns out there are a lot of like real-life examples of cross-sections. Bread, a lot of machine parts like screws and nails and stuff like that are very much cross-sectional. Just in a crazy amount. Like if you're on robotics, you probably realize like so many of the parts you used have either rotational symmetry or cross-sectional symmetry. Even the ancient Mayans used symmetry, rather cross-sections to build their pyramids and that sort of thing, like Chichen Itza here. Which technically wasn't a pyramid, if you want to get technical, but, you know, whatever. Let's move through these a little bit. Okay, the last kind of question that I really wanted to make sure I did was a question like this. Yeah, Nick, no worries, dude. I'm just basically ignoring everything from you right now. Because that's where our buddy Dogi is. Alright, the last kind of question I want to look at that didn't show up in the notes was what if you have a rectangle? Because we hadn't looked at rectangles. We had looked at both kinds of triangles, squares, and semicircles. But what if we do rectangles? Now, this one has rectangles with heights that is 3 times the base. We have two functions, 6 and x squared. It's the shaded region below, so also we start at 0 here. We are doing perpendicular to the y-axis here, so actually our rectangles are here. Like so. Going up into that direction. Which means I'm going to have to solve these equations for x, but there's really only one equation, and it's really easy to solve. So, booyah, done. I solved for x. Which means this distance, the x distance, because this is the x coordinate of the curve, is the square root of y. Sweet. I'm going to go to build my integral. Now, the integral is base times height. Cool. I got to find these pieces. So base is the square root of y. Height is 3 times the base, so it's 3 times the square root of y. My equation's in terms of y's, because we're perpendicular to the y-axis, so dy. And our y values start at 0 and go to 6. And now all we do is root y times root y is, okay, this one's very easy to do by hand. We're integrating from 0 to 6 of 3y dy. I integrate, get 3y squared over 2 from 0 to 6. And I plug in 6, and I get 3 times 6 squared over 2, which is 54. And that's it! So rectangles are pretty easy. Now, there is another type of rectangle, and it actually would have been harder here. This one was made easier in that the height was 3 times the base. But they could just give you a rectangle with height 7. So if I did the same problem with a rectangle of height 7 instead of a rectangle with height 3 times the base, the only change in my integral would be it'd still be integral from 0 to 6. Base would still be the square root of y, but height would just be 7. And that would be my integral. And so it's not harder in the case where you have a numerical heights. It's actually an easier equation. In this case, it would have been a harder integral, so thankfully it wasn't that. But yeah, pretty easy to build that equation, even if it's just a static height. All right, so this is cross-section. So, hey folks, any questions about cross-sections that I can answer before I show you what the homework is and we call it here? I finished like right on time. It's 2. Killing it. Even with things going on. because I mean the homework's on AP Classroom. I put like 8 of these questions on there, so it's shorter than a lot of the other AP Classroom assignments. So these are a little more involved a lot of the time, so I wanted to make sure it was a little bit more attainable. There is no attendance document this time, Daikun, and other people, because there is an assignment. Groove's happy, cool. Tim showed up like 3 minutes before the end, nice. Tim, if you're struggling with this at all, we did do the notes for cross-section, and anybody that showed up late, we did do the notes for the cross-section, so you can go through and look at that, or copy the ones off my website, and those might help. Hey, all of you who got spoofed, I still love you guys. No worries. I'm not taking any of that stuff personally. Once I realized it was you guys are cool. Seniors, make sure you do assignments right now and turn in all your assignments so that when I change your grade, I change it to as high as possible. I was going through and looking at doing that, and a lot of seniors have a lot of missing assignments. So, dear seniors, please do all your missing assignments if you want your grade to go up. And many of you should want that. Yeah, you guys, in general, are awesome, and I'll see you next time, which will be Thursday, which we'll start talking about revolutions, which probably is easier than this, just FYI. This is one of the hardest things, so, yeah. Alright, bye-bye.